Hello everyone, I'm Lele from Centre for Digital Music, Queen Mary University of London. This is a video recording for our paper at ISMIR 2022, Performance MIDI-to-SCORE Conversion by Neural Beat Tracking. This work is conducted as an internship project at ByteDance with my mentor Qiuqiang and also under my supervisors Veronica Morfi and Emmanouil Benetos. I'd like to thank the Alan Turing Institute for their support to my work through an enrichment scheme, and the MCDT and the CSC for the support to my PhD study. In this paper, we focus on the problem of performance MIDI-to-SCORE conversion. It aims to convert a MIDI performance, usually recorded by electronic MIDI keyboard, into a music score in computer-readable format. It can be useful in various scenarios such as music improvisation, complete music transcription, and music performance analysis. In this work specifically, we focus on transcription of a performance MIDI into a MIDI score. Performance MIDI-to-SCORE conversion covers a list of subtasks. Over the years, people have proposed various techniques for each of the subtasks. For example, the use of hidden marker models for rhythm quantization and neural network methods for note value and voice estimation. We propose to use a deep learning method for PM2S with a compact output representation, including quantized onset times and note values, time signatures, key signatures, and hand parts. We pay special attention to the rhythm quantization step and propose to solve the problem by tracking beats on a MIDI note sequence. We compared different input encodings of MIDI note sequences and did some ablation studies on input features and data augmentation methods, and have released the code for PM2S conversion as a toolbox. We define the problem as shown in the slide. Given the pitch, onset, duration, and velocity of each note in a performance MIDI, the PM2S model aims to get the musical onsets, note values, hand parts, time and key signature changes for a MIDI score. We consider the prediction of musical onsets and note values as the rhythm quantization step. We consider rhythm quantization as a hierarchical problem that can be combined by beat and downbeat tracking and beat subdivision prediction. For beat tracking in a note sequence, we consider the beats that are concurrent with note onsets as in-note beats and others as out-of-note beats. They are predicted in two steps. For in-note beat prediction, we use a CNN model where the model input is the note sequence and output is the probability of each note being in beat. In the left figure, you can see the detailed model structure for in-note beat prediction. And for out-of-note beat prediction, we use a dynamic programming method. We design an objective function to be minimized based on music knowledge that encourages a low level of tempo change and add fewer out-of-note beats. We set a penalty coefficient, lambda, for adding out-of-note beats. This coefficient is tuned based on experiments. We further expand the CRNN model to the prediction of score information using a compact output data representation. To do this, we distribute the time and key signatures to be mapped with each note by their onset times. We group the prediction of beats, downbeats, and tempo as the three of them are highly related, and use the information from beat and note value prediction to help the prediction of musical onsets. The holistic model architecture is in the figure, where the convolutional blocks and GRU blocks have the same model architecture as the ones in the CNN model in the previous slide. In our experiments, we use a collection of classical piano performances and scores from three sources: the MAPS dataset, the classical piano MIDI database, and the ASAP dataset. Due to the lack of note level alignment annotations in the ASAP dataset, we use it for beat and downbeat tracking only. We split the train, validation, and test sets in a way that they do not have overlapping pieces. Following this, our experimental dataset statistics is in the right table. There are in total 504 different music pieces in 123 hours. We use 29 performances from the MAPS dataset for testing, since they are commonly used as testing set. To begin with, we did some comparative experiments on bit tracking in performance MIDIs. We first tried to find the best input data encoding combination by making a comparison between each of them, that is, encoding pitch as one-hot vectors in its MIDI pitch number or pitch octave values, encoding onset time as one-hot vectors or raw values, and in the form of absolute or relative timing, encoding note duration as whether one-hot vectors or raw values. For velocity, we normalized all of them to the range of 0 to 1. This results in 16 different input encoding combinations. The comparison is based on the performance of in-note bit tracking, and the results are shown in the right table. From the results, we can see that the use of MIDI pitch relative onset in one-hot format and duration in raw values resulted in the best model performance in terms of note level F measure. Using the best input encoding combination, we did 2 ablation studies on the input feature and on various data augmentation methods. Still, the model performance are reported for the in-note bit tracking task and in-note level F measure. Results are in Table 3. According to the results, all the 4 input features are beneficial to the prediction of bits. Also, the data augmentation methods we used, pitch shift, tempo change, note removal, and extra note, all help to achieve a better bit tracking performance. Combining our in-note bit tracking model and dynamic programming method for out-of-note bit prediction, we further compare our bit tracking system with a retrained baseline model in a temporal convolutional neural network architecture, and whose model input is changed to binary piano roll. Table 4 shows the performance on different output data. It shows in the table that our proposed model significantly outperforms the baseline. We finally checked the performance of our system on our end task, performance MIDI-to-SCORE conversion. Here, we use the MV2H metric for comparing 2 MIDI scores. We compare our proposed PM2S model with 2 commercial software, say Finale and MuteScore. Both of them provide functionality to import a MIDI file and convert it to a music score format. We report all the 5 submetrics on MV2H. You can see the results in the right table. It shows in the results that our model achieves overall better performance than the 2 software in all submetrics. A significantly better performance can be observed in metrical alignment due to our method's ability to track tempo changes. We have made our paper, code for the toolbox, and example and demo available online. Any feedback or comments will be very appreciated. Thank you.